Good morning, my dear students. Today's topic is carbonyl compounds, lecture number 4. So, carbonyl compound is started in lecture number 1, 2, and 3. We have covered some chemical reactions. Now, the next remaining reactions are here. So, first reaction is alpha substitution reaction in carbonyl compounds. If sp3 alpha H is present, then it can substitute by deuterium or halogen. So this is the reaction, alpha substitution reaction. So first I take the alpha halogenation. Halogen substitution reaction, that is alpha halogenation of carbonyl compounds. It is possible in both medium. So first in acidic medium, only one alpha H can replace by halogen. Generally chlorine, bromine and iodine is taken. Second, in basic medium, all sp3 alpha H can replace by X, replaced by halogen. Again sp3 alpha H. So example is like this. Suppose I take RCO CH3, CH2 CH3. This is the alpha carbon. Br2 acetic acid, it is the acidic medium, or bromine water is taken, or you can write Br2OH minus. So RCO CHBr CS3, only one hydrogen is substituted in acidic medium. Now in basic medium, both hydrogen is replaced by halogen finally. So I repeat the reaction, alpha substitution, that is alpha halogenation of carbonyl compounds. In acidic medium, only one alpha H can replace. In basic medium, all sp3 alpha H can replace by the halogen. So through enolization, this reaction takes place. So this carbon is alpha carbon, it is sp3. So in acidic medium or HOBr, you can write Br2 plus water means HOBr, that is again acidic medium. So only one H is replaced. But in case of basic medium, all the hydrogen atoms are replaced by halogen. Some important points for this reaction is, suppose reaction is electrophilic substitution. Of halogen. Now mechanism. In acidic medium, intermediate is enol, RCO CH2 CH3 H plus Br2. So enol is formed. Now this enol react with the bromine as an electrophilic reaction. And this Br minus takes away this hydrogen. So after removal of HBr, one hydrogen is replaced. This is in acidic medium. So intermediate is enol. So through enolization it is possible. But after adding one bromine or one halogen, then again enolization takes place very difficult or slow. That's why the second halogenation does not take place in this case. So rate of enolization now rate of enolization is further slow down in acidic medium. So only one halogenation takes place. Now be in basic medium. RCO CH2 CH3. Fast acid base reaction takes place. So remove the alpha H. Now on reaction with bromine, RCO CHBr CH3. So one bromination takes place. Suppose this is the rate R1 and it is known as rate determining step. Now again OH minus, or suppose this is the rate R2. So acidic strength of this hydrogen increases because of minus I. So R2 is faster than R1. In R1 acidic nature is less, but in case of R2 acidic nature is more because of minus I effect. So R2 is faster than R1. So reaction does not stop in between. That's why all the alpha hydrogen replaced by halogen. Important point is rate. R1 is slower than R2. Second important point, rate of alpha halogenation does not depend upon type of halogen. So rate with respect to halogens is Cl2, Br2, I2. For all the halogen rate is same in basic medium. So I repeat the mechanism in basic medium. First remove the alpha H in basic medium. Carbanion is formed. Now carbanion takes bromine as an electrophilic type of reaction. So bromine, one bromination takes place. Now the acidic strength of alpha H increases because of bromine. So again it remove very easily. C minus again take the bromine and dibromo or tribromo products are obtained. So major important part is rate. First step is RDS. R1 is less than R2, or you can say step 1 is RDS. Rate of alpha halogenation does not depend upon the type of halogen. Here, these are the fast step, so it does not depend upon the fast step. So rate with respect to halogens are same as per Cl, bromine or chlorine. Now some examples. Question number 1. Br2NOH. So all alpha H can replace, but in the same time, if I take Br2 acetic acid, then only one hydrogen is replaced, and that is site where the enol is more stable. So enol is more stable at this point, so this hydrogen is replaced with halogen atom. So this is the final product. Br2 is in excess amount. Question number 2. PHCH2CHO. Cl2 H plus Cl2 KOH. So this is the result. Now the next reaction is haloform reaction, haloform test. Or you can write iodoform test. This is next type of halogenation. In this haloform reaction, COCH3 group must present in the compound, or we can take the secondary alcohol. If I take X2 plus OH minus in basic medium, or you can write NaOX or KOX or XO minus, then acid salt plus CHX3 is obtained. CHX3 is the haloform, and acid obtained having one carbon less than the reactant. So it is very important reaction. So I repeat the haloform reaction. Haloform reaction or iodoform test, we can take halogen, either chlorine or bromine or iodine. So if iodine is taken, then test is known as iodoform test. If bromine is taken, then test is known as bromoform or haloform test. Haloform is the common general name. So which can give haloform reaction? The COCH3 or CHOHCH3 present, then only haloform reaction is possible. So alcohol first oxidized into ketone, then only the same reaction takes place. So halogen in basic medium, or you can write sodium hypohalite, potassium hypohalite or hypohalite ion. Then the CO part convert into acid and the CH3 convert into haloform. So this is the reaction. Now come to the mechanism. Mechanism of haloform reaction. Suppose I take the RCOCH3. First step, suppose NaOH is taken, then first hydrogen is removed. This is the R1 step. RCOCH2 minus is obtained. Now in second case, halogen is taken. So one halogen is removed as NX and first halogenation takes place. Now this reaction repeat. Suppose I again take NaOH, that is suppose R2 and again X2. So second halogenation take place. R2 is faster than R1. Now next, again NaOH, suppose this is R3, next X2. So tri-halo product is formed. Now this is a good leaving group. So it react with NaOH directly and mechanism is SN to TH. So in SN to TH, leaving group removes and CX3 minus is formed. But one is acid, one is base. So H plus exchange between both of them. So final product is SCO minus and CHX3, it is halo form. So this is the mechanism. It is the same mechanism as it was in basic medium. So here R1 is slower than R2 is slower than R3, or suppose I take this is R4, so it is slower than R4. So overall R1 is the RDS. R1 is the RDS step. And the next important point, reaction does not stop after mono or di halogenation. It goes up to halo form. So total 3 moles of halogen and 4 moles of base are required for this reaction. So total moles required is, you can write moles of X2 is equal to 3, moles of base is equal to 4 for 1 mole of reactant. So total 3 moles of halogen and 4 moles of base are required. If I take limited amount of halogen or base, then reaction proceed till the end point, but complete reactant could not be converted into products. Now question number 1. PHCOCH3 I2NOH. So final product is sodium benzoate plus CH I3. It is a yellow orange precipitate. That is iodoform. Bromoform is liquid, brown color liquid, and chloroform is the gas. So generally iodoform is used to distinguish or identify the compound in the lab. Suppose question number 2. Same reaction. This is the acid plus iodoform is obtained. Question number 3. First, suppose ozonolysis takes place. So this is produced, both are COCH3. So after reaction with, suppose, iodoform in basic medium, plus CHI3, two molecules. So these groups are present or responsible for the iodoform test. COCH3 group must be present in the iodoform reaction. Now come to the next part, D exchange at alpha carbon. It is the same reaction. There is again electrophilic substitution reaction. For example, suppose acetone is taken, and in presence of OD minus D2O, or D plus D2O in any medium, either in basic medium or in acidic medium. First, suppose one hydrogen is replaced by D. This is the first product through enolization. Process is through enolization. So one deuterium is replaced. Now if I proceed the reaction OD minus D2O an excess amount for a long time, then all the alpha hydrogen atoms are replaced by deuterium. So finally 6 deuterium exchange is obtained in this reaction. So you can solve the few examples. Suppose second example, how many D exchange are possible in this reaction? Suppose OD minus D2. So how many D exchange are possible? So identify the alpha position. This is the alpha position. So only one hydrogen is there. So finally one H is exchanged with D. So this is the final product. In this case, there are 2 alpha positions and total 3 hydrogen atoms are present. So total 3 deuterium exchange is obtained in the final product. So this is the D exchange. D exchange is an electrophilic substitution reaction. Again, it is through enolization. Now this is a part of alpha halogenation. Now I start the next reaction, that is very important reaction, conjugate addition. So next title is conjugate addition. It is known as 1,4 addition reaction. So it is possible in conjugated system. Possible in conjugated system, conjugated carbonyl compounds. Now, for example, This is a conjugated compound. Alpha, beta, carbon are unsaturated. So this is a conjugated system. In this conjugated system, there are two resonating structures possible for this. So I write the two resonating structures. First, R CH double bond CH O minus, this is R. Second, if I move this pi bond, so R CH plus CH double bond C O minus R. So two different additions are possible in this molecule. So first, nucleophile add to the carbonyl carbon and electrophile on H. This is known as 1-2 addition because both atoms add on the adjacent position. But in this case, nucleophile add to this carbon and electrophile or H plus add to the oxygen atom. So it is 1, 2, 3, 4. So it is known as conjugate addition, 1-4 addition. So this molecule gives 1-4 addition and this molecule gives 1-2 addition. So both are possible in this compound depending upon the situations or reagents. Which type of nucleophiles are present? So in general, hard nucleophile, hard base, hard nucleophile, hard base prefer 1-2 addition, and soft nucleophile, soft base prefer 1-4 addition. So I classify the examples after the mechanism. So please see the mechanism of this reaction. One four addition mechanism. RCH COR. Resonating structure is like this: R CH CH double bond C O minus R. So on reaction with nucleophile go to the carbon of alkene. In the next step, H plus taken from the water molecule. So RCH CH double bond COH R and nucleophile add. Now this is known as 1-4 addition, 1 and 4, or you can write 1 and 4. But this is the enol. So enols are generally less stable. So after tautomerization, it is converted into ketone. So hydrogen transferred to the alpha carbon, and this is the final product. So in 1,4 addition, nucleophile add to the 4th carbon, electrophile add to the oxygen, but after enolization or tautomerization, this is converted into ketone. So overall, please see the difference between the reactant and product. So reactant has one alkene and one carbonyl group. But in this product, carbonyl group is as it is, but alkenes give addition reaction. So final comment for this reaction is addition takes place at the pi bond of alkene. Next, product is thermodynamically more stable. So it is known as TCP. So reaction is follow TCP, thermodynamically controlled process. Generally ketones prefer 1,4 addition. Also soft base or soft nucleophile prefer 1,4 addition. For example, SH minus, ROH, NH3, RNH2, RCH minus CHO, R2CuLi, RCU. These kind of nucleophiles prefer 1,4 addition generally. So I repeat the mechanism of 1,4 addition. It is possible in the conjugated system pi sigma pi. When I write the resonance structure, means the partial positive at 2 carbon atoms, one is there and one is here. So nucleophile attached to the carbon of alkene atom, and O minus take the H plus, that is 1,4 addition. It is enol, finally tautomerize into ketone. Final product is this. In the final product, C double bond C of alkene give net addition reaction. So that's why I write here addition takes place at the pi bond of alkene. It is a thermodynamically more stable product because C double bond O is present but C double bond C is absent. So thermodynamically this bond is stronger. So overall product is more stable. So reaction is known as TCP, or product is also known as thermodynamically controlled product or thermodynamically controlled process. Generally ketones prefer 1,4 addition and soft base prefer 1,4 addition. Soft base like SH minus, ROH, ammonia, amines, C minus, that is carbanions, R2CuLi, RCU. Those kind of nucleophiles prefer 1,4 addition. Now I write 1,2 addition. Mechanism of 1,2 addition. So in case of 1,2 addition, nucleophile add to the directly carbonyl carbon. Hydrogen goes to the oxygen atom. So you can see here addition takes place at the adjacent position, that is 1,2 addition. So this is the final product, there is no enol. So this is the final product of this reaction. So this is thermodynamically less stable. So addition takes place at the pi bond of carbonyl. It is kinetically controlled reaction. This reaction is faster than the previous one. So product is less stable and it is kinetically controlled. Kinetically controlled process or reaction is KCP. Rather than TCP, it is a KCP. Generally, aldehydes prefer 1,2 addition. Hard base or nucleophile prefer 1,2 addition. So hard base like this, lithium aluminium hydride RMgX RO minus NaBH4, like compounds prefer 1,2 addition reaction. Now I repeat the same. 1,2 addition means addition or on the same adjacent positions. So in this case, pi bond of C double bond O give net addition reaction. Nucleophile directly attack to the carbonyl carbon. So this is the final product. It is simple nucleophilic addition reaction. Product is less stable and it is kinetically controlled process. Reaction is known as KCP. Generally, aldehydes prefer 1,2 addition. Hard base like lithium aluminum hydride, Grignard reagent, RO minus NaBH4 prefer the 1,2 addition reaction. I come to the questions. Question number 1. CH2 double bond CH double bond O. This is the conjugated aldehyde. It is a very less crowded aldehyde. So aldehyde generally prefer 1,4 addition. So suppose I write lithium aluminium hydride in presence of ether, or here I write suppose D2O. So first H minus goes to the carbonyl carbon. It is a hard base. So 1,2 addition is prefer. Final product is CH2 double bond CH. Here is H and D. This is the final product. Suppose I take pH MgBr, then H2O in presence of ether. Again, this is 1,2 addition. Suppose I take KCN, H plus. So it prefers again 1,2 addition. So these all are 1,2 addition reactions. But if I take the SH minus, so it gives 1,4 addition. So in case of 1,4 addition, nucleophile add to the fourth number of carbon atom. So this is 1,4 addition measure. Now come to the next question, question number 2. Suppose I take a ketone, example of ketone. So this is a conjugated ketone pi sigma pi. So the same reagents are taken. Suppose lithium aluminum hydride and D2O, or you can write lithium aluminum deuteride. Then deuterium goes to the ketone. So it is 1,2 addition. Prefer 1,2 addition. Similarly, I take CH3 MgBr followed by water. So it is again 1,2 because it is hard base. But suppose I take CH3 whole twice CuLi. So it gives 1,4 addition. So this is 1,4 addition. In the same question, suppose I take KCN. So it is again give 1,4 addition. So this is the difference. So in general, aldehydes prefer 1,2 addition, ketones prefer 1,4 addition, but it also depends upon the nucleophiles also. Now the next question is like this. CMe3. So this carbonyl compound is highly crowded. So this is highly crowded. So in this case, Grignard agent also give 1,4 addition because of crowding effect. So this is the exceptional or important type of example. So in 1,4 addition, methyl add to the here. This is the major product. Now another example is like this. CH3 whole twice CuLi. Then it is again 1,4 addition, but there is a one methyl group above the plane. So it attacks from below the plane. So that's why trans isomer is obtained. So this product is major. So crowding effect is again dominating effect in 1,4 addition reaction. Now the next very important example is like this. So in this case, alpha hydrogen is present. It can give aldol reaction. So first I write the anion, the first step of aldol. Now suppose if this molecule is given. Now this is category as a soft base. So give 1,4 addition reaction. So in case of 1,4 addition, pi bond of alkene give net addition reaction. So I add this pi bond CH2, CH2, CO, CH3. Now this is the final product. But in basic medium, it can give intramolecular aldol reaction. So again in basic medium, can give intramolecular aldol reaction. So this negative charge remove the alpha H. This is the first step. CH2, CH2, CO, CH2 minus. This nucleophile give addition to C double bond O 1, 2, 3, 4, 5, 6. 6-membered ring is formed by intramolecular aldol reaction. So OH group is here. Now double bond is here. After heating, in basic medium E1CB mechanism takes place and the water eliminates. So after elimination of water, we get alpha beta unsaturated carbonyl compound. This is alpha beta unsaturated carbonyl compound. This example is important example. Now I take the another similar type of example that is known as Robinson annulation. This reaction is known as Robinson annulation. First aldol at 1,4 addition, then second aldol by intramolecular reaction, then this is known as Robinson annulation reaction. Annulation means ring formation takes place. One other example is like this. Suppose this is the compound. In basic medium, sp3 alpha H is removed. So CH2 double bond CH, CH double bond CH, CO, CH2 minus. So in this reaction, intramolecular 1,4 or 1,6 addition takes place. This is intramolecular reaction. So this pi bond is shifted like this. So total 6-member ring is obtained. 1, 2, 3, 4, 5, 6. Suppose I write the numbering. Now here again I write the numbering. 1, 2, 3, 4, 5, 6. So double bond between 4 and 5. Another double bond between 2 and 3. Now O minus OH at the carbon number 2. This is enol. So this enol tautomerize into ketone. This is the final product. Sorry. Okay, this is the final product of this reaction. So lecture is carbonyl compounds. Lecture number 5. Miscellaneous reactions are there. So first is Tishenko reaction. Tishenko reaction is the modified reaction of Cannizzaro reaction. In the Cannizzaro reaction, products are acid plus alcohol. But in Tishenko reaction, product is directly ester. So all aldehydes give this reaction in presence of strong base, that is aluminium tertiary ethoxide like of base on heating. So aldehydes have alpha H or does not have. All converts into directly esters. So this is the acid and alcohol. So if Cannizzaro reaction takes place, then one part is acid, another part is alcohol. So after esterification, this ester is obtained. But in this reaction, directly ester is obtained. So this is the first example. Now come to the second. CH3, CH2, CHO, then CH3, CH2, CO, OCH2, CH2, CH3. This is the product. Now third example is like this. Suppose I take this kind of aldehydes, that is dialdehyde. So it is directly converted into ester. So aldehydes having alpha H or does not have alpha H all directly convert into ester. This reaction is known as Tishenko reaction. The next reaction is Wittig reaction. The Wittig reaction, alkenes are prepared. So it is a preparation of alkenes by carbonyl compound plus Wittig reagent. So general reaction is like this. I take a carbonyl compound RCHO. This is known as Wittig reagent, or we can write phosphorus halide. These are the name for this reagent. So on reaction, RCH double bond CHR. I write suppose R dash, so this is R dash. And the next is OPPH3. So this oxygen is exchanged with this group. So this is the reaction, Wittig reaction. Mechanism is like this. RCHO R dash CH double bond PPS3. So PPS3 gains the electron like this. A cyclic transition state is obtained. This is a cyclic transition state. So after the rearrangement, suppose rearrangement is like this. These bonds are broken. So RCH double bond CHR dash plus OPPH3. These are the product. Wittig reagent can be prepared by halides in basic medium with PPS3. So next is preparation of Wittig reagent. One degree or 2 degree halides you can take, either 1 degree or 2 degree halides. On reaction with PPS3, triphenylphosphine, ascent to reaction take place. So RCH2 PPS3, this is the product. In presence of base, this H is removed, so RCH PPS3. This is also written as CH double bond PPS3. So this is the Wittig reagent or the phosphorus halide. Now some questions. Suppose this aldehyde ketone is given, CH2 double bond CH2 double bond PS3 is given. So after complete the reaction, this alkene is obtained. So in this case, the oxygen is replaced by CH CH3. This is POPPH3. So this reaction is known as Wittig reaction. Wittig reaction is used to prepare alkenes from the carbonyl compound plus Wittig reagent. Wittig reagent is also known as phosphorus halide. So it is very simple reaction. Exchange the oxygen with this group. Now come to the next reaction. Benzoin condensation. Reactants are aromatic aldehyde, KCN plus strong base. Products is the benzoin. PHCHOH. This is known as benzoin. So general reaction is like this: PHCHO plus, there are 2 moles of benzaldehyde on reaction with KCN, alcoholic KOH, that is very strong base. So final product is PHCHOH COOH. This is known as benzoin. So this is a general reaction. Now mechanism. KCN attack to the carbonyl carbon. This is a nucleophilic addition. CN minus attack to the carbonyl carbon and it is converted to O minus. Now H exchange. So after rearrangement, this H is obtained by the oxygen. This is more stable carbon ion. So it rearranged into this. It is resonance stabilized with benzene as well as with CN group. That's why this is more stable and it act as nucleophile. So it give addition to the another molecule of benzaldehyde. So after addition of the another molecule, I get this compound. In this compound, this O minus take the hydrogen, convert it into pi bond and CN act as a leaving group. The cyanide act as a leaving group. So overall PHCHOH COPH. This product is obtained. So I repeat the mechanism. First, cyanide attack to the carbonyl carbon. Then cyanohydrin type of product is formed. Then in a strong basic PDM, this O minus shifted to the C minus and then C minus act as a nucleophile. Carbon is better nucleophile than oxygen. So it attacks to the next molecule of aldehyde and after addition, this is the compound and by H exchange, this pi bond is formed and cyanide is removed as a leaving group. So benzoin is obtained. So particularly this reaction is known as benzoin condensation reaction. Now next reaction, benzylic acid rearrangement reaction. So PHCOOPH, this is known as benzyl. In basic medium on heating gives benzylic acid. This rearrangement is known as benzylic acid rearrangement. It is possible in benzyl type of compounds in strong basic medium. So mechanism is this. This is the general reaction. PHCO, COPH. This benzyl can be obtained by the oxidation of benzoin. Benzoin has a one alcohol, one ketone group. So after oxidation with PCC, we get the benzyl. Basic medium, one OH take to the carbonyl carbon. So this is the product. Now the O minus again form the double bond. Then pH transfer to the next carbon. This is the rearrangement. And after H plus exchange, acid can lose, base can accept the proton. So after exchange the H plus, we can find the product. So this is the benzylic acid salt. So it is again similar to the Cannizzaro reaction. In Cannizzaro reaction, hydride transfer takes place, but there is no hydride in this molecule. So that's why phenyl transfers, and after the transfer of phenyl group, then this product is obtained. So I write a question. This is again similar to the benzoin. Only difference is this bond is attached. In the benzyl, this bond is not there. So same type of reaction. Again, when making the pi bond, then this benzene ring shifted to the next carbonyl carbon. The 5-member ring is there. So it is converted into O minus, and this is converted into COOH. So after exchange, H plus exchange, product is COO minus, and this is OH. So this is the benzylic acid rearrangement type of reaction. So next reaction is preparation of urotropin. Urotropin is the antiseptic. It is used as a medicine. It is a urinary antiseptic, urotropin. So next is preparation of urotropin. 6 moles of formaldehyde plus 4 moles of ammonia on reaction with acidic or basic medium, it gives urotropin. Structure of urotropin is like this. So 6 CH2 molecules are there and 4 nitrogen molecules are there. So it is a condensation type of reaction, and this is known as urotropin. Urotropin is used as antiseptic. urinary antiseptic. Now next reaction is reduction of carbonyl by PCl5. So all the carbonyl compounds reduced by PCl5 and converted into RCHCl, that is same dihalide, and the byproduct is POCl3. The next reaction is preparation of DDT. Dichloro-diphenyl trichloroethane. It is an insecticide or used as pesticides. It is non-biodegradable. So it is banned. So for DDT, chloral is used with chlorobenzene in presence of acidic medium. So 2 molecule of chlorobenzene is required. Reaction is electrophilic aromatic substitution type of reaction, EAS reaction at the para position of benzene. So this hydrogen is removed. So taking the 2 molecules, 2 hydrogen atoms are removed with 1 oxygen atom. So net water molecule is removed. So CCl3CH. So 2 benzene ring connect from the para position to the Cl. This is known as DDT. Full form of DDT is, or IPSC name of DDT is 111 trichloro 2,2 bis parachlorophenyl ethane. So numbering is like this. So 111 trichloro 2,2 bis parachlorophenyl ethane. This is the IPSC name. Our common name is dichloro-diphenyl trichloroethane. Next, reduction with magnesium and mercury. So acetone on reduction with magnesium and mercury converted into pinacol. Their 2 molecule condense with each other and this product is formed, that is known as pinacol. It is the natural alcohol which obtained in the some cases. The last is the lab test of carbonyl compounds. The last is the lab test of carbonyl compounds. So all the carbonyl compound gives 2,4-DNP test. All carbonyl give yellow, orange PPT with 2,4-DNP. The next test is tolerance test. aldehydes give tolerance test. Reaction is like this. All aldehyde on reaction with AgNO3 in basic medium oxidize into acid, and Ag plus 1 converted into Ag0, that is the silver mirror. Or you can write black precipitate. The third is fouling test. In fouling test, reagents are there are two reagents, solution A and solution B. Solution A is the copper sulfate, that is copper in +2 state. Solution B is sodium potassium tartrate. It is also known as Rochelle salt. So overall copper 2 plus react in this reaction. In basic medium. So reaction is like this: RCHO, copper 2 plus in presence of basic medium, aldehyde oxidized into acid or copper reduced into copper plus 1. This is the red PPT. Cuprous oxide. The D is Benedict test. So it is again the same test. Reagents are again solution A, solution B. Solution A is same, copper sulfate. Solution B is sodium citrate. So acid is changed. So reaction is again same reaction, aldehyde on reaction with copper 2 plus in basic medium converted into acid plus cuprous oxide, means copper reduced, aldehyde oxidized. So red precipitate is obtained. Only aliphatic aldehydes gives fouling and fouling Benedict and shift test. Aromatic aldehydes does not. So these are the lab tests of aldehydes and ketones. Now I summarize the all carbonyl compounds. So in carbonyl compound there is a important reaction is nucleophilic addition reactions. So we have discussed all the nucleophilic addition reactions. Nucleophilic addition with Grignard reagent, cyanide, sodium bisulfite, water, alcohol, ammonia and ammonia derivatives. And then nucleophilic addition in aldol reaction, and similarly nucleophilic addition in Cannizzaro reaction, as well as in Perkin reaction also. So all reactions gives the same type of mechanism, that is nucleophilic addition. And other reactions are Wittig reaction, Tishenko reaction, benzoin condensation, benzyl benzylic acid rearrangement, and very important reaction was haloform test. So thank you.